can see those red. So you can see the profile, okay? You can see the profile. So for each case, the hole depth is much higher, but we also see some deposited material at the edge, right? For both cases, this we saw especially for graphene. So for gold, most of the cases, the material that we deposited, you know, they were vaporized. But for graphene, because it has a strong, you know, carbon chain, so you are breaking down that carbon chains, and then those carbon chains are curling. Okay, so you have that. So if you look at here, in the first picture, so you have all those carbon, you know, honeycomb structure, and you have carbon. So when you are machining, you are breaking some of those carbon, okay? And when you are breaking, like just consider you have a net, metallic net, and you are cutting the net. What happened to the other portion? It tries to curl, right? So very similar thing it happened here. So you have the network with carbon, and when you machine, you broke, you know, some of those network, and remaining it tries to kind of, you know, go back. So we saw most of those deposition for when we machined graphene, but not, you know, when we machined atomically flat gold. But there is still some vaporization, because you can see the depth is much higher than the deposited material, and we found that about, you know, 30 to 40% of the material were evaporated and remaining material were deposited, okay, to the wall. And we also see some kind of, you know, heat affected zone also there. So as I mentioned, volume of the deposited material was 50 to 70% of the volume of the removed material, and a remaining percent was evaporated. So we can say that both melting and evaporation process actually took place, and we can see a little bit of recast layer formation at the edge of the nano hole for machining graphene, but we didn't see that actually for machining gold, atomically flat gold.
How do you confirm that that's a recast layer?
So that's a very good question. So I think most of the cases from here, when there is a color change, that also indicates some kind of, you know, phase change, okay, on the surface. So I think from there we are able to, you know, get that information. But I remember that we were also able to collect some other information in those zones than here. Yeah. So that kind of tells you that there is some change in those, you know, like in that material compared to the parent material. Yeah.
So that thickness of that graphene.
So I think those thickness of the, so usually one layer of graphene is about 300 nanometer or something like that, but it has multiple layers of graphenes. Yeah, so all those holes are blind holes. Yeah, not through holes. Those are blind holes. Okay. Okay, now you see here, we were able to get much sharper image here. So heat affected zone and surface reconstruction. So as I mentioned, we were able to, you know, see some heat affected zone, you know, for both cases, as I mentioned, you know, by looking at the color. See, those color, you know, doesn't always indicate the deposition of material. There are some deposition of material, but as I mentioned, we were able to collect some other information. I think that color change is directly an effect of the temperature change also. Okay, so and also some kind of phase transformation. So we are able to kind of, you know, see some of those heat affected zone and recast layer. But we also saw that there is some reconstruction that is also in, like, how to say, a criteria, not criteria, a signature of the graphene. Okay, so it tries, yeah.
Sir, why it is not uniform? Like there is a certain kind of geometry from this side and this side. That recast layer or color change.
What do you mean by what is not uniform?
That golden yellow color, sir.
Mm-hmm.
Left and
Okay, so let me tell you. So what happened either from picture 1 to 3, it shows that after some time. So first picture, second picture, first picture is without, second picture at 0 minute after machining, so immediately after machining. Second, like number C is 30 minutes after machining, and number 4 is 1 hour after machining. So what we can see that the depth, is slightly reducing, right? And like the heat affected zone is also, reducing or spreading out. So that's what I said. So we saw that there is some slow reduction of the diameter and the depth, right? So that's what we try to tell here. So this is kind of we observed during machining of graphene, because graphene has a tendency to reconstruct, okay? So that's what we saw here. There is some reduction of the depth and diameter, and heat affected zone also gradually decrease over time because of the reconstruction of carbon lattices in graphene. So that's the kind of characteristics of the graphene, and we found that if you do machining in the graphene, it happens, okay? But the holes were permanent. So now we observed for 1 hour, and after 1 hour we found the hole. But I don't know what happens after 1 day, right? In 1 day, graphene may be able to reconstruct fully, right? But that's something you like future research needs to study, okay? Okay, so now we continued some machining areas of holes, and we also found for some cases we see lots of deposited materials at the rim of the nano holes with reduction of bias voltage. Then, okay, so what I'm saying, I used higher bias voltage like 3500 millivolt, 1 nano ampere for 5 seconds for the first letter. And we found that there are definitely more material removal, but there are some, like heat affected zone and deposition. But when you reduce the bias voltage and also pulse duration, it tries to kind of give you more controlled machining, okay? Okay, now let's talk about dry nano EDM. We did some more studies, so if you go back to some of the papers, you may find some more study, okay? Okay, so now let's talk about dielectric. So for dielectric in micro EDM, usually you supply some air into the gap because the tool is going into the electrode. But here, tool is not going into the electrode, it always stays there. So air is already covering the space, right, if you are not using any dielectric. So we just use that air that is already there, and then all other things we just kept it same. Now, when you select the bias voltage and current, you need to have actually enough field to break down the dielectric, and the voltage required to break down the dielectric is actually smaller than N decane. So N decane, it was 1 times 10 to the power 9 volt per meter, and here it is 3 times 10 to the power 6 volt per meter. Okay, so that means whatever bias voltage I was using for machining under the dielectric liquid should work here also, right? Okay, so the mechanism you applied the bias voltage to bring the field strength above the breakdown strength required, then it is going to create some heat when you break down the air, and then that will create some field induced evaporation of ions. So for this case we used, we are creating the field strength of about 1 times 10 to the power 9 volt per meter, which is much higher than the breakdown requires. So we found that there are a lot of evaporation for dry EDM, and also there are some melting process happening as we analyze the tool, and then material removes from here. Okay, now this is something that I found, and later we kind of make this standard for in situ tool fabrication. So what I found that if you use wet nano EDM, most of the cases after breakdown, the tool gets blunt, right? But if you do dry nano EDM, there are more evaporation, taking place in the dry nano EDM compared to the wet nano EDM, and those evaporation actually helping the tool material to sharpen itself. So that means if we start with the tool material that has multiple asperities, okay, and then if you do dry nano EDM for some time, every time you do dry nano EDM, there are some evaporation, from the tool, okay, and that actually helps to kind of make the tool sharpen. And we proved that. We use the tool, and then we kind of did some dry EDM and take out the tool, did the analysis, and we found that the tool quality gets sharper and sharper. And then definitely at some point, if it is like 20 nanometer, after 20 nanometer, that portion kind of breaks. No, I would not say breaks. That portion kind of melts and it becomes blunt again. Okay, but the thing is, in the dry nano EDM process, you should be able to kind of use the dry nano EDM to like dress the electrode. Okay, that means in situ electrode dressing, you can use that dry nano EDM process. Okay, now how I showed that? So I used the same tool. I got a tool, okay, I fabricated a tool, I put that into the tool holder, then I did some analysis of the tool quality, and it showed, by looking at the graph, it shows that this is quality 3 tool, and I tried to do some machining. Half of the features didn't really come out very well. Then once I did machining one time, okay, so after machining about 50 to 100 features, the tool quality improved a little bit. So I got this in the second attempt because the tool quality improves. Then third time, when I checked the tool quality after machining, these 2 steps, I forgot how many features here. You can probably count, but I think it's in between 50 to 100 features. So after machining 2 times, the tool quality becomes very good, okay, because of that in situ, tool sharpening, and I was able to get, this NSF written very well, okay. All the holes were very sharp, circular, well defined, and because the tool quality was improved. So now you see, I started with the tool quality 3, and I ran some dry EDM, trial and error, okay, and that helped, to sharpen the tool. And once I am confirmed that tool quality is 1, then I can do the final step machining that I want. So that's something, we found, like I would say, I kind of developed later on. So now here you see very good, hole quality for this. So I tried to machine just 1 letter with some holes, and you see those grain boundaries, right? All those are grain boundaries. This is grain, all those are grain boundaries, and you can really see that all the holes came out very well defined. Now here we analyzed individual holes, right? So when I take a line for 3 holes, you can see all the holes are same depth, right? All the holes are same depth, and like those cone shapes, okay? But one thing is, by looking at the shape, don't think that the tool went inside, because the tool is about 30 nanometer, 20 to 30 nanometer, but the hole size is about 10 nanometer. So the tool never went into the hole, but it is the electric field, that kind of, created those features, right? So now here you can see the whole features is very uniform. So we can measure the depth, we can measure the diameter, then from there we can actually measure the material removal rate. Now here I did some repeatability analysis for all the holes. So it is 50 holes actually in the NSF word. So you have X direction, Y direction, Z direction. So mean hole size I found about 7.5 to 8 nanometer, okay, and the depth we found about 0.6 nanometer, so less than 1 nanometer. Standard deviation was about 1 nanometer for the diameter and depth 0.1 nanometer. This is for the statistical analysis for 50 holes that we did. And spread percentage, so overcut, how much overcut? About 17, 17%. And the minimum features we found 5 and maximum 10. So that is something also, is scope for future research. So although we use same energy and also same pulse duration, the feature size varied from 5 to 10 nanometers. So that means improvement needs to be done here. Okay, now consistency in material renewable rate, very consistent. So if you look at number of nanoholes machined and volume removed, it follows a very good trend, right? So that means for some cases, if you see that the diameter is slightly smaller, maybe the depth actually covers that. So the depth is higher. So volume removed for individual features are very similar, okay? And that's why we got it, very similar. So you see, first 10, the material renewable rate, next 10, next 20, 30, 40, 50. Now we kind of investigated what could be the reason, and we have a valid point. We are not using any, like linear guide for movement, right? We are using piezo. So for piezo, some directions is the movement, is outside. I would not say easy, but some direction the movement is more accurate than some other direction, because it's a material, piezoelectric material, right? So it may move in this direction very well, in this direction very well, but when it is moving at an angle, maybe the movement is not that good, and that could be the reason for the variation of the feature size that we saw. Okay, and also you see the material renewable rate, it should be same for all, but slightly varied, from first 10 feature, next 10, next 10, next 10, something like that.
Sir, you measure the MRR, so for the first 10 holes, then second, next 10 holes. So how you measure? Means,
So you can calculate the volume, right?
volume.
And then you have that, time that you use. Yeah.
Generally, experimentally, we measure by weight.
But here we measured by looking at the profile. So from the profile you get the diameter and depth, right? And it is cone shape. So I use cone formula for cone to get that. Yeah. Oh, so now we tried the capability, right? So if we can machine NSF, then why not we try to machine some other things, right? So this is USA. We try to machine. Again, you see the grain boundaries, and machining is happening in the each grains and grain boundaries. So this is USA. We have written. Then my supervisor asked me to kind of create a USA map. So I tried to create USA map, but unfortunately there is some grain boundary here, and you see that it is not atomically flat, right? So the surface roughness, that's why I said the surface roughness should be atomically flat, and the surface roughness was not flat there. So we can see some grain boundaries here, and it is not fully flat, so some portion didn't come out very well. So this is kind of, you see some holes where we tried to machine holes on top of those holes. It didn't really come out well, but for other, actually it did really come out well.
Sir, in the point of the holes, nano holes, so the fluctuation in the IZ graph you observe?
So IZ curve we only took before machining to check the quality, and after machining. And after machining, most of the cases, if it is dry machining, the quality is still there, but if it is wet machining, the quality went down. So, and one thing I should tell, when we run the nano script, you create the program for the entire one, and then when you hit like apply, it tries to complete the entire thing. So that means for each point it will go there, and then it will apply the bias voltage, current, and the pulse duration that you are supplying or you are coding, and then it will go to the next position and do the same. Okay, and it will do the same. So sometimes we found that I'm sure there could be some limitation on how many features you can make, because if there are more features, then you will see more variation in the diameter and all those things. Okay. Okay, so tool quality, as I mentioned, tool quality for So for tool quality for white nano EDM, tool quality decreases from quality 1 to quality 2 after machining about 100 nano features. Because most of the cases we found that for white nano EDM, the melting actually process dominates, so that kind of creates the make the tool blunt. On the other hand, for dry nano EDM, we found that the field induced evaporation actually dominates, okay, and that's why the tool actually becomes better. So the tip quality improves after machining 100 features, and if it further improves after machining 150 features. So that sharpening of the tip tool can be done in dry nano EDM, and I used to follow that once we develop the process. Even if we did white EDM, we use dry EDM first to run several times to improve the quality and check the quality when it is Q1, then we did white EDM. Okay, so that's what we did. So this is something kind of new. And in terms of quality, dry EDM, white EDM, we also found that because dry EDM field induced evaporation is the main mechanism, we found that for the same energy the hole size is slightly smaller, and more, I would say, controlled when you use dry EDM compared to white EDM. So in the dry EDM, for the same program nanoscript we run, we found that dry EDM is about 7.5 nanometer hole size, whereas white EDM is about 10 nanometer hole size. So, and white EDM has more variation. You see for the N, some of the holes are not shallow, right? Here some of the holes are shallow, some of the holes are shallow here, some of the holes are deeper, but here most of the holes are almost of similar depth, okay, and diameter. So the variation is less, and here it shows actually the variation. So for wet and so this is for liquid dielectric with liquid dielectric. So this is for mechanically sheared, chemically sheared, and mechanically sheared with dry nano EDM. Okay, so this is something also interesting. We know at the beginning I said the mechanically sheared tools are not good, but we found that if you use dry EDM, you can actually use mechanically sheared tool for longer time, because it goes through some tool sharpening. So now you can see for mechanically sheared tool, if you compare that with the mechanically sheared tool for white EDM, the minimum feature size 7.5 to 8.7, 8 to 10, depth is much higher, 0.6 to 0.4. The variation is also smaller. So for mechanically sheared tool, definitely dry EDM is outperforming that liquid, or traditional EDM in terms of feature, analysis. But for nano EDM, if you do with electrochemical etch tool, okay, and for white EDM and for dry EDM, then electrochemical etch tool performs better. So that means for electrochemical etch tool is still is good. So if you do dry EDM with electrochemical etch tool, then that would be the best solution for you. Okay, this is also comparison of the material renewable rate. Mechanically sheared tool with dry nano EDM outperforms even electrochemically etched tool for traditional white EDM. So that means dry EDM can really get you in terms of better or better feature quality in terms of higher material renewable rate and less variation, right? So now this is again comparison of white nano EM and dry nano EM. So this is the importance. That could be one of the reasons. Maybe if we used, for white nano EM, if you use higher field strength, right, maybe white nano EDM will also perform better. But what we did is not a fully fair comparison. For white EDM and dry nano EDM, we used kind of the same parameters, but remember the field strength is much higher for white nano EM. On the other hand, dry nano EM, the field strength required is lower. So you need lower field strength, but I applied much higher field strength. But for white EDM, I just barely applied like 1.1 in place of 1. So maybe if you apply higher field strength for white nano EM, just like the same way we applied for dry, it may also perform better. Okay, so this is kind of nano electromachining based on scanning tunneling microscope. Okay, so now I'm going to present nano electromachining based on AFM. So the good thing is for STM it is electrically conductive, right? So the setup is very, I would say, very much similar to the die sinking, so you need less modification, right? But for AFM, if you use now, AFM also has conductive AFM, okay? But previously when we were doing that research in 2009-10, that time it was not there. So for AFM, you need to kind of connect to a pulse generator, and then you need to supply the voltage. So here AFM based nano EM, so very similar. The difference is STM tool is vertical, very similar to conventional micro EDM tool. But for AFM, you cannot really make the tool by yourself. You need to purchase that tool. You saw AFM tool, right? AFM tool has a cantilever, then it has a sharp triangle here. Like triangle, it looks like triangle, but it is not triangle. So yeah, so it's a tip, right? Silicon nitride or some kind of diamond tip. Now, if you use that for EDM, your tip cannot be diamond tip. It has to be silicon nitride or electrically conductive tip, right? Yeah, so you can actually use the AFM, then connect two ends of the AFM to the pulse generator so that you can supply the electrical pulses, and then all of the things are same. You use oscilloscope, to collect the information, and AFM controller will control the AFM. Okay, so very similar thing. Electrically conductive AFM probe needs to be used, as I mentioned, and the tool as a tool for the nano EM. Then you have atomically flat gold or copper, film as a workpiece, and then it used actually deionized water. So this time it was done by the deionized water. So this is done by Professor Rajvikar group, but we were on the same group, but his student tried just slightly different than what we were trying. So the deionized water instead of andecan. So that means here the workpiece was changed, the tool was changed, and the system was changed, but it also worked. So that means you can modify either AFM or STM to do the nanoscale EDM process. Okay, so how it was done, experimental procedure. Remember, for STM based one, we used scanning first of the surface that we are going to machine, so that we can actually get the information about the surface. But AFM, you need to engage in contact mode. So AFM contact mode means, that's why most of the nanoscale mechanical machining processes has been done by AFM. Okay, that means nano milling, lots of work on nano milling. So you use the AFM tip to contact the surface, and then scan it to get the information, and then you scan size, you change to the 0. When you change the scan size to the 0, that means it is on a spot, right? On a position, desired position. Then you set the gap distance. Okay, so there are some difference from STM based. So you set the gap distance, manually how far is the gap distance needs to be. Then you apply the voltage to the tip and workpiece, and then you again increase the scan size, and then you try to do some scanning here. Now the problem with that is sometimes AFM tip actually, if it gets, I'll show you in one picture, it gets melted. So then you need to take note of the position, put a new tip and come back to that position to scan. But STM sometimes allows you to take the pictures just after machining. So here you see the AFM tip is no more sharper, right? After you see this, here I can show. So usually your AFM tip was like that, okay? The AFM tip was like that when they did the machining, but because of the melting process, the AFM tip becomes melted, right? And it becomes burnt. So now look at the feature. The feature is very similar to what we saw in the nanoscale using STM process. So you can actually calculate the volume of that feature considering this as a cone, right? And they also did some analysis of this, analysis of this, and they found some kind of modification on the tool tip as well. Okay, so material removal mechanism, they actually offer several hypotheses. First hypothesis, they said hammering effect due to the electrostatic force between the tool. So hammering effect means you have very sharp, and then that happens. So you have a very sharp tip, right? And you are supplying very high energy with that sharp tip, right? So it is kind of a hammering effect. You are using very large energy, you are trying to pass through a very sharp point, okay? So because of that kind of very large hammering effect, it kind of that sharp tool melts away. Then you can also consider very similar to hypothesis that we gave, field induced evaporation. We can also say that, okay, very similar. You are applying the voltage so that they use some dielectric also, I mentioned, right? Deionized water. So when you are using some electric field, you are creating electric field to break down that dielectric, right? And when you break down that dielectric, any breakdown of the dielectric creates some kind of heat, right? And that heat can also melt the tool material that we saw. So that means we can say that it's kind of very similar mechanism of STM based processes, okay? And also it shows there is some decomposition, the workpiece was copper and the tip has some copper in it also. So that means it tells you that at the dielectric interface there is some melting and there is some transfer of material from the tool and the workpiece. So very similar thing happened for the EDM or micro EDM.
So it is a contact process. So
No, contact process was used for scanning only. After scanning, we took it out and then applied. Yeah, then you supply the voltage. Okay, yeah, it is not contact process. But AFM itself is a contact process. STM, remember, the tool goes down and comes very close to the atom, okay, and it interacts with the, make a channel with the atom and interacts. But AFM, it is a contact process. It goes and contact the surface and it gets information by tapping and getting forces. By that difference, it tries to give you a picture. On the other hand, STM, it doesn't contact, but it gets the current from that atom, and from that it gives you the image. Yeah.
But you are performing the AFM through AFM. It is a contact process. So how are you maintaining the gap?
So you are not doing AFM that time. So you do AFM to contact and get the scan. Then you stop it. You bring that scan size 0 so that it is not moving. It is staying at one point. Then you bring that tool out. So you bring that tool out, and then you put the dielectric and you apply the voltage. Okay. Okay, so here it shows, the AFM tip was used as a scanning also, right? So that's the good thing about AFM also, and STM, because it can do some scanning also. So here you can see there is some vertical, incline, and square groups that were machined on copper film using the AFM-based nano electromachining process. All those are non-contact process. Remember, the tool is not contacting the workpiece, right? Then they did the very similar to what we did, tried to machine some arrays of hold to get some features, and also some slots, okay, using the nano EM process. Okay, any question? Okay, so the last one, what is the time? Oh, we're a little bit over, right? Yeah, but nobody told me. Okay, so I'm finishing in 5 minutes, then we are going to do some, and then we are going to leave. Okay, so nano electrochemical machining, that means nano ECM. Very similar arrangement. All you need to do is change the dielectric, right? You need to change the dielectric and put some electrolyte there, okay? And then you do that, you will see the ECM process, okay? So that's what it happened. You use the electrochemical, nano manufacturing, AFM. The same AFM you can use for ECM process. All you need to do is you need to submerge that, interface, in a fluid sample, in electrolyte. So here, then the duration of the current applied to the electrode is reduced, and the electrochemical reactions can be confined within close proximity of the electrode. So if you put the too much duration, then it can probably spread. So you apply the duration of the current for a shorter time, so that the ECM process is happening at the close proximity. And it says at nanoscale, the fundamental application, fundamental operation is very similar mechanism of electrochemical reactions like Faraday's law, but it also includes some little bit of analysis, some little bit of changes like electrochemical transformation and some anodic oxidation. So it's kind of slightly different. So here it shows the nano ECM process. So now how do you know this is nano ECM? You see the electrochemical dissolution also makes the edges not so sharp. For EDM it was sharp. If you just go back few slides, look, yeah, the first one, look here, those are very sharp, right? The edges. On the other hand, for electrochemical dissolution, same problem. It is not sharp, okay? So ECM process doesn't really give you very sharp corners. So then you will be able to get some nano groups. So this is everything kept similar, just few changes. You change the dielectric, put the electrolyte, and then you change the pulse duration, to bring, and you can play with the voltage and current. You don't apply as much as high voltage that you are applying for the EDM process. Okay, so that's kind of the summary. So remember, I mentioned I'm just covering the electromachining processes like EDM and ECM at nanoscale. But there are researchers who have done lots of research on nanomechanical milling. Okay, they used AFM to contact just like milling process, and they come up with different tool geometry. So if you are interested in that, you can get a lot of paper on that as well. Okay, but those are mostly the nanomachining processes. Others are like lithography based processes, mostly for polymer and silicon, and there are some other process like focused ion beam, then electron beam, laser, that can also give you some nano features. So those are some of the nanomachining processes. Okay, so now just few future research opportunities. So none of the research have been done on hybrid nanomachining. As I mentioned, I was planning to start that area, but unfortunately I did not, but I still have the plan to do, when the additive will get a little bit saturated, I will start, kind of nanoscale hybrid, processes. Nano ECDM, nobody has done that, so you have done micro ECDM. So nano ECDM is a process kind of to explore. ECDM, yeah. Then one of the major challenges is industrial grade machine. We use AFM, right, to modify. So that's something you need to consider. You know, maybe you can modify AFM or STM, but then come up with a design that is, you know, sellable. Okay, that you can actually bring it to the industry. Another thing is XC2. I forgot to mention here, XC2. You should be able to kind of locate it after you take out from the part. So there are some research needs to be done where you machine that and then you bring that part and you should be able to locate those. And also we did some nano machining. We monitored for you know, several hours, and we say that features are permanent. But honestly, if the features are permanent, if I cannot show that XC2, nobody will trust, right? So there are some research needs to be done in those areas also, right? So understanding physical principle, like there are a lot of things can be analyzed, like physical principle, material interactions of atom with tool, workpiece, then liquid, medium, behavior of the materials at nanoscale. All those are needed in order to develop new techniques, okay? So modeling of the machining at nanoscale is one of the least explored area, and you can always do some modeling of what you are doing, okay? So thank you everyone. So I'm going to stop here. Any question?
Sir, real-life application of the nano product.
So real life application is there. So as I mentioned, like there are some nanolithography on the polymer and silicon, and that's why we see all of those in our cell phone and all others. So applications are there. It is not just electrical, it is not just metal. I'm not sure about metal because after 10 years, I'm you know, presenting something on nanoscale machining, maybe already in the market. You know, you can use FIB probably to machine some nano features on the metal thin film. Yeah, so probably in market already there. So if you want to develop EDM, you know, you can develop EDM, and then you need to compete with some other processes now. But hybrid processes, I don't think nobody worked on those processes. Yeah. Okay, yeah, so we can talk about that. So I have a small quiz for you. So you know, let's take that quiz. So you saw the ECDM process in the lab, and I covered in the theory. So I have a short question on how ECDM work, and then I have some like 10 MCQ multiple choice questions, and I think all of you will be able to answer those. Yeah, you can also distribute.